It's time to start. So we are talking about reinforcement learning, and today we'll be talking mainly about solving MDP. And last time we were introducing reinforcement learning, and we are talking about this simple worldview where we have an agent. The agent is submitting some actions to the world, and after each action it gets some observation of the new state of the world and some reward signal. And the goal of the agent is to optimize the reward signal, so it's like much more autonomous learning. It requires much less input data instead of some like examples of inputs and outputs, which can be complicated. You just have a simple reward signal, like what do you want the agent to optimize. And also, like these methods can learn during the lifetime of the agent, so it's not like you have a training set and some training regime where you pre-train the agent and then you just run it. You can do it that way, but it's not necessary. You can learn and act at the same time, so you start acting in some suboptimal way, and during this learning process you will be improving and eventually, hopefully, converge to the optimal solution. And we are talking about MDPs, that Markov decision processes are the main model used in reinforcement learning, which is a set of states, rewards, actions, and this kind of dynamics, which is fully probabilistic and gives us a probability distribution. If in state S we perform some action, what is the next state we'll get and what reward we'll get, right? And we draw it as these graphs where we have states in which we can make some actions, and when we make the action, there is a probabilistic transition to some new state where we can perform new actions. And we were talking about, at the very end of last lecture, policies, that in these MDPs we'll be searching for policies which are mappings, probabilistic mappings against from states to probability distribution over actions, and they can be probabilistic or deterministic. Usually they are probabilistic, and reinforcement learning is trying to specify methods, algorithms, how to improve this policy based on new data, new experience, in order to maximize the reward over the long run. And we are talking about what the over the long run means, that it can have different definitions, but the most commonly used, which we'll be using all the time, is discounted sum of rewards. So sum of rewards from now until forever, weighted by this gamma discount factor. Okay, so that was the last lecture. And in this lecture, we will introduce value functions and Bellman equations, which are like some of the very fundamental concepts of reinforcement learning, but we'll not be doing reinforcement learning yet, because we'll be assuming that we know this MDP. That means that we know the set of states, we know the transition function, we know like what happens if we perform some action in some state, what are the possible next states with what probabilities and so on. So that we call known MDP, and we'll basically just come up with algorithms that compute the optimal strategy in these known MDPs. And in the next lecture, we will go to full reinforcement learning setting, where we will assume that we only have access to a simulator, so you can only interact with the world as the agent would naturally interact with the world, because the known MDP is kind of fake, right? Like if you are in a real world, you know that you can perform this action, and when you perform it, you will see what was the outcome. You rarely know that, okay, if I perform this action, like robot will move one meter ahead, that there is like 92% probability I'll end up 1 meter and 5 centimeters, and there is 1% probability that I'll end up 95 centimeters, and so on and so on, right? Like it will just happen. You'll try it in the world, and the world will give you the observation where you ended up, but you rarely know the model, the exact model of the MDP. But now, for this lecture, just to start with something to explain the algorithms, we'll assume that we know the MDP. So in next lecture, we'll be learning like despite of not knowing the MDP, and we will very briefly touch on how you can scale these methods using neural networks and talk specifically about the DQN agent, which was like the first super popular, super successful deep learning agent which was able to play the Atari games. Any questions? To the previous lecture, to homeworks, anything at all I forgot to ask at the beginning? No, everything clear? So let's dive into it. Value functions. As I said, value functions are one of the most fundamental concepts in reinforcement learning, and they are functions from states to rewards. If you just say state value function or just value function, you usually mean the state value function for a specific policy, right? So the input, even though we often write it as an index here, it's still an input to that function. And then another input is the state, and the output will be the expected return. The expected return is the G. The returns are how we aggregate the rewards, right? So the G can be the discounted sum, and the expectation means like if I follow the policy from this point, from this state, infinitely many times, like what will be the average reward I'll get by using this policy from this state, right? So that's the expected return. Sometimes it's convenient to define a different value function, which is called action value function or Q function. And that's a function, again, that has an input, the policy, the state, and an action, and returns a reward of if I am in the state, I perform the action, and then I continue based on the policy pi, whatever it is, right? The Q is, again, expected return. If I am in state S, perform some action A, and then continue pi forever. Okay, we can draw some super simple example to make it a little more interactive. So I wanted to call this S1, S2, S3, S4, and it will be a deterministic MDP, which will, for each step, if we bang our head to the wall here, we'll get -1. Otherwise, for each step, we'll get -0.1. We want to get to the goal, to the right, so for that step, we'll get 10. And if we are going the wrong way, like here, if we continue, it's fine. We can do whatever, we'll stay in that state. Here, if we go the wrong way, we just pay the -0.1, and here we pay the -0.1. Is the MDP clear? How it works? So you can imagine is a robot, let's say, in some narrow corridor, it can go right or left. Every time it goes anywhere, for each step it pays for energy, and then it wants to get to S4, and then it's happy in S4 and stay there. And it doesn't want to hit the wall and go somewhere where there is no place. So now we need a policy. So let's say we have a policy 1, which says always right. Then what would be the value of pi1 in state S1? Right, it's the value for being at state S1 and then following the policy pi1, which says always right. So you will go right, you will go right, you will go right, you will go right, right, right. And you want to compute the expected return. You need the discount factor, right? So let's say for now, just for simplicity, the discount factor will be 1. So we don't care about the discount factor. So what will be the value in that state? 9.8, right? Because we get minus 0.1, minus 0.1, and 10. And that's our like expected return. We can have a different policy, policy pi2, which is always left. What will be the value function of pi2 in state S2? Minus infinity, yes. Because we have the discount factor of 1. What if we had discount factor of 0.9? Does anyone remember the high school algebra? What would be the value function of pi2 in state S1? So we'll get minus 1, right? Gamma times minus 1, gamma squared times minus 1, and so on. Which is minus 1 times sum from whatever 0 to infinity gamma to the power of n, right? And the sum of geometric series is something like that, right? So with the 0.9, it would be like minus 10, roughly. Okay, but these are simple deterministic policies. What about the policy P3, which is uniform left and right? What will be the value function? So let's say that we want the value function by 3 in state S3. And it will be mess to compute, right? But what you can say is that, so you are in S3, you are uniform, so with probability 1/2 you would go here. From probability 1/2 you would go here, right? And you can say that the value function is 1/2, you will get a 10, plus 1/2, you will get, immediately you will get minus 0.1, right? And then plus gamma times value function for pi3 in state S2. Right? Because the value function is what happens if you are in that state and you follow the policy pi forever. What is the expected value? So if you are in a state 3 and play that policy forever, that's like you make one step of that policy and you play it forever, this is 0, that's why I didn't have to write it. Or you make one step here, and then you run the policy from there forever, which is exactly the value function in that other state. Does it make sense? Okay, so these value functions are super important, and they will be part of all of the algorithms we'll be working with. That's why I spend more time to really demonstrate what they mean. And they are often implemented as arrays. So the value function for pi1 would often be an array where you have, it's indexed by the states of S1, S2, S3, S4, and you put in the values. So here it will be 9.8, 9.9, 10, and 0. Value function for P2 would be a similar array, which is minus infinity, minus infinity, minus infinity, and 0 with the discount factor of 1. Okay, so that's value function. The action value function is similar. So what would be the action value function for pi1 in state S2 and right? Again, we perform the action right, we pay minus 0.1, and then we'll play based on pi, which is going right all the time. From here, it will get 10. So it would be 9.9. Okay. Now, if we have these value functions, we can define a partial ordering on policies using the state value function. And we would say that policy pi is, or pi prime is better than a policy pi if and only if for every single state that policy is better, like the value function for that policy is better than the value function for another policy. Right? So here we can say that pi1 is better than pi2. Right? Because for every state, for this state it's better, for this state is better, for this state is better, for this state is better, like better or equal. So pi1 is better than pi2. The optimal policy, does it need to be unique? Do you have just one optimal policy in MDPs? Or can you have many? Any ideas? Who thinks that there is an optimal policy for any MDP, just single one unique optimal policy? No one? Who thinks there are many different optimal policies? Most of you, perfect. So how would we show that? So we have some kind of a start state. We can go up and down to the goal state. We can go down and up to the goal state. Right? We can pay like -1, and here we'll get the 10. And we can have this policy with probability 1, and this policy with probability 1, and they are both optimal policies, right? They will get us to the state to the goal state as quickly as possible. So, okay, that's why you didn't think, because I already put it there. So there are multiple optimal policies. What about the value function? Is there a single optimal value function, or can even the value function related to the optimal policy be different? So if there is something like the optimal policy, and we say that this partial ordering will be ordering policies, then the best policy should be better than all the other policies, right? And if the value functions were different, it wouldn't really work, right? Because the policies would lead to different value functions. So the optimal value function is always the same. So here, if we have these two policies, one goes up and the one goes down, the value function for, like here, it would be 10, for here it would be 9, right? If we go this way, here it's a little undefined, right? Like here depends whether you would go this way with your policy. Then it wouldn't be the optimal policy, right? Then you would have the value of that state 8. But if you go this way, you have the value of that state 10, and it's the optimal policy, regardless of whether you go this way or this way. If you have the policy even in the states where you don't get correct, then it's still the same optimal value function. Why is it partial ordering? Can you think of two value functions which will be, or two policies, which value functions will be not comparable? Mm-hmm. What I was thinking about is a very similar example with additional edge here. So if you go like this, you would have like 10, 9, 8. If you take a different color and you go like this, then you will have 10, 9, 8. Right? So you have two policies. They are both suboptimal, and they have different value functions which are not comparable. Right? Because in this state, the green is better than the white. In this state, the white is better than the green. Right? So none of them is better than the other. But if you go to the optimal one will have another color. The optimal value function will be just 10, 10, 9, right? And that will be dominating all the other policies. That will be better than the green one and better than the white one. So optimal policies share the same optimal state value function. That's important for theory if you want to prove that it converges something to somewhere. And optimal policies also share the same optimal action value function, which is not that difficult. So if you make one step and then you continue doing the optimal thing, then the value function will be the same. So that still holds. Did I want to say anything more here? No. So in this example, the P1 was the optimal value function. The P1 was the optimal policy, and we denote the optimal policy by pi star and the optimal value function by V star. Okay, so why do we care about optimal value functions? Why is it so important concept? And that's because once you compute the optimal value function, it's rather easy to compute the optimal policy. Right? If you just evaluate all actions, Like this is a type of formula you will be seeing for the next 2 lectures quite often. So I know that they look ugly for the very first sight, but they are actually not that scary if you think about them a little. So you take the best action, and you take basically the expectation over all possible next state and rewards. So you will take the transition model. This is the probability that you will get to state S prime. You will get reward R if you are in state S and perform action A. You will get a reward, and you will get gamma times the optimal value function of the following state that you will reach. And if you compute this for all actions and you pick the best action, you are greedy with respect to the value function, and you are performing the optimal policy. Any questions? And now, if you think about this formula, like what would it look like with the optimal Q function, the optimal action value function? Like why I would claim that optimal action value function is often much more convenient. So why is it more convenient if you think about that? Like, would you rather know this V star, or would you rather know Q star if you were to implement this agent? Like this is basically the Q star, right? Is the expected value of performing action A in state S. So the advantage is that you don't need to compute all that. But it has another huge advantage, not only that you can like save some computation, but there is like a very fundamental difference why in many cases you can use the Q function, but it's very difficult to use the V function. And that's exactly the known dynamics, right? We are assuming here for this lecture that we know this probability distribution, but in reality, this is exactly what you will not know, right? In reinforcement learning, you want to learn a good policy even though you don't know the dynamics. And if you are learning the Q function directly, then you will just pick the action in current state which has the highest Q function. You don't need to actually make this like one step look ahead to compute the expected value of that action and then pick the action. You can pick the action directly based on the Q function you are computing. And also, like the multi-unbanded setting that we were talking about last time, you have just this like one state. So this is much more natural representation, and that's why we are talking about the Q values in that lecture, because it's the same like Q value function. Okay. So we know what are the value functions and what they are good for. So now let's talk about how to compute them, right? And this is, again, one of the most fundamental equations of reinforcement learning, which is called Bellman equation for policy. And again, it looks a little scary, but I kind of sneakily try to push it to you here already, right? It's just a generalization of what I was trying to show you here. It just says that if you want to compute the value for a state, you can take the expectation over all actions you can perform in that state and take the expected value of that action, which is expectation over all possible next states and rewards, the probability that this will happen times the immediate reward plus gamma times the value function in the state where you are entering, right? So again, I remember that I was kind of not happy to read these formulas, but once you get into them, they are not anything complicated. And this is actually a set of equations, right? If you think about that, if you create this Bellman equation for every single state, this is a variable, this is a variable, all the other things are constants. If you assume that the policy you are evaluating is constant for now, then it's just one equation per state with one variable per state, right? So if you have n states, you have n equations with n variables. They are all linear, so you can just solve them using any kind of solver for a set of linear equations. They are often, because there are very many formulas like this, which differ in very small details, and is not convenient for everyone to read them in the formulas. That's why the book and the reinforcement learning community sometimes uses these backup diagrams, which are just graphical representation of those formulas, right? So it would say that in order to compute the value function for the state, you will take the expectation over all the actions, you will take all the rewards, like all outcomes of those actions, and you will take the expectation over all of that. If you want to compute the Q function, you will take, again, for state and action, you will take all possible outcomes, what reward they get, and in that outcome, you will again take expectation over all possible actions. So I don't have the value function for the Q, but you can imagine based on this backup diagram how it would look like, right? So again, it would be sum over all the outcomes after this action, the probability of that outcome and that reward, plus what is the following reward, and the following reward is the expectation over the Q function over all the actions you can perform in the following state. Questions? Is it clear, or should I repeat it? Yeah, definitely. Thank you. Thank you for the question. So pi is generally the policy that the agent is following, right? So v pi in the index, you are evaluating what is the expected value of the policy pi in state S. You will look at all the actions which are applicable in state S and take the probability that you would take that action in that policy, right? So this is probability of action A in state S. And then you sum over all possible outcomes it can have, right? So if you are the robots, you are in some state, you decide to go 1 meter ahead. The possible outcomes could be that you will actually go the meter, you will go 1 meter and 5, or you will go 95 centimeters, right? These are these S primes. There are different possible outcomes of that action in that state. And you will get different rewards possibly for each of that outcome. And then you sum over all possible outcomes. And in each outcome, you will get the reward plus the gamma times the value function in that state where you transition using that action. And these pictures just like represent these formulas. So this allows us to simply compute the the values for a policy, right? That's an important task. Can we use it the other way around? Can we give it a policy and give it values and want to compute a policy? Right, based on some kind of mechanism, we computed the value function, and now we want to compute the policy. Sure, yeah, it's again a set of linear equations. Like now, these will become constants. These will be the only variables. They are there in a linear form, so you can compute back also the policy from the value function. And that's why it's such a fundamental concept, because you can just transform value functions to policies and back using this. Okay, so here is an example of the backup. So it again follows the backup diagram. If you have the robot on a slippery floor, which is trying to get to the goal, your policy can be down or right. Like you go down 2/3, right 1/3. If you try to go down, there is 90% probability that you will succeed and you will get the reward. And there is 1% probability that you will slip and you will stay where you were. And you will not get a reward. And here, again, with this lower probability, you will succeed or fail, but you are not getting any reward anyway. So if you take an expectation from all of these, then it will be like 2/3 times 0.99, right? Times 1 will be the value function of this one. Okay, so that was an arbitrary value function for arbitrary policy, right? But we don't care that much about arbitrary policies. We care more about the optimal policies. And there is a Bellman optimality equation for V star, for the optimal value function, which just says that optimal value function is created by taking the optimal action in each state, right? So optimal value function for a state will be the max over all optimal Q functions. And if you just write down what that means that you want to take the best action now, and then you want to continue following the optimal policy, right? So it's rather simple. You will take max over all actions. You will look at what are the outcomes of the actions, compute the expected outcome of that action using the optimal value function, right? So you assume that you are looking for the best action now, and then you will continue optimally, right? And that's why you will reach this V star. So this can be again denoted by this backup diagram, where we use this curve to say that it's max. If there is no curve, that's expectation over the options. If there is this curve, that's just max, right? So that's useful for someone. And now the V star, which is already something we care about a lot, right? Because if we have V star, then we can trivially just be greedy with respect to V star, is a unique solution of this system of equations. Can we easily solve this system of equations? What do we remember from optimization? Yes, that's a very good answer. So usually in optimization, we talk about linear things, which are nice, and everything if everything is linear, everything is easy to compute. When anything becomes nonlinear, almost every time it becomes hard. Like then rarely you have some special cases of like strongly convex functions and whatever, where you can still have some polynomial guarantees, but it becomes hard, and max is definitely not a nice function. So this is generally not easy anymore to just solve using any kind of generic optimization solver. And that's why there are like specific algorithms that are designed to solve this, basically this system of equations. And that's called solving MDPs. So you can write a similar optimality equation for Q star, right? So for Q star, there will be expectation over like making that action and then continuing based on the optimal policy. And if you continue based on the optimal policy, that means that you will get the reward now. Like again, like remember the notation of the book. Large capital letters are random variables. So if you have the expectation and then you have this RT plus 1, that means that like it will have different realizations, but you take expectation over all the possible realizations of this variable, right? And then you take gamma because you are in the next step, and you take the best action right. This is just the best action in the following state. Based on the Q star, based on the optimal Q function. And again, the state you will end up in is a random variable. That's why it's capital, because for different for the same action, you can end up in different states just based on the random outcomes. So it's this kind of expectation. If you roll it as a sum, it's sum over the dynamics, the reward that you get, and the optimal action that you can perform in the following step. And again, it's a system of nonlinear equations, so you could solve that. It corresponds to this diagram, so you take expectation over the outcomes, and then you will take max over the following actions. And if you can solve this, you are done. You have solved the MDP. Questions? Okay, last question about the value functions. So is there any relationship to the A algorithm and A star algorithm? Right there, we were also working with some values of F, G, H. Do you remember what it was? Like what would the... Exactly, right? So the optimal value function basically corresponds to the optimal heuristic, which would just take us to the goal if we follow it greedily. But in MDPs, everything is harder because very often they are stochastic, right? So the outcomes are stochastic, and there the analogy already doesn't work so well. So how do we solve this optimal Bellman optimality equations? We need the accurate knowledge of the environment. We have enough space to do the computation, right? So how much space do we need in general for MDPs? I can tell you that the computation will eventually be, or could be, polynomial in the size of the MDP. So that's kind of all right. That's usually what you want from algorithms. But what does it mean? How large are the MDPs usually? Right, like very often they are exponentially large in all sorts of inputs. If you have just a robot in the maze, that's all right, that's polynomial, right? Because the robot can be at any position. But if you have some more complex robot with joints and angles of each of the legs, then every configuration, every possible combination of positions of their joints is a new state possibility, right? So very often the size of the MDP is combinatorial. If you want to model like game of Go or chess or something like that as an MDP, if you fix the opponent, you can do it, right? But again, all combinations of pieces are new states. So the amount of states is often exponential, but solving the optimality equations can be polynomial in that state. So most of reinforcement learning methods actually can be viewed as approximate solving of these Bellman optimality equations. And then we can come up with the first procedure that does that, which is policy evaluation prediction. So now let's say we have the policy pi, and we want to compute the state value function for that policy, right? We were doing that rather intuitively here, and we said that, okay, we can compute it using this system of equations, but that's hard. There are easier ways. So recall what we want to compute. This is the Bellman equation, right? And we will do it iteratively. We will just apply this Bellman equation as an update operator on the value function, and we will see what happens, right? So we'll do so-called a sweep. We'll take the value function as it is, and then we will apply these operators. So we will just use the equation as it is, but here we use the old value function, and here we are computing the new value function, right? So it's the same formula. The expectation over actions you can take, expectation over what can happen, reward, gamma times the value function in the following state. But we will compute a new value function based on the old value function. So just to understand, I'll show you an example on the simple grid world where we have actions up, down, left, right. For every move, we'll pay 1, right? As usual, these are the terminal states where you want to get, and you are getting the penalty of -1 until you reach the final state, right? So you want to find it as quickly as possible. And let's take a uniform value function, right? Now in this kind of grid. So we initialize it randomly, or we can initialize it any way we want, but let's say here, for simplicity, we initialize it by zeros. And then for K1, for the first value function, we will look at this cell, right? It's this cell. What actions we can do? So we can go up, right, left, and down. For each action, let's say it's deterministic, so we will just move to the following state. We will get the reward of -1, and we will get the value function in the following state, which is 0, 0, 0, 0, right? So we put here -1. Then we do it for the next one. Like for this one, the same, 0, 0, 0, 0. The expectation is -1. For here, right, we would compute all of these. And then we will start to use K1 as the old one and K2 as the new one. And again, we want to compute this value. So it will be with probability 1/4 we will get this, with probability 1/4 we will get this, with probability 1/4 we will get this, with probability 1/4 we will get this. So this will be -1, the reward will be -1, gamma is 1, right? So we will have here -2. Why is this different? So again, with 1/4, we will go here, which is 0. With 1/4, we will go here. With 1/4, we will go here. And if we go left, I didn't say that, but it was written there, you get -1 and you will stay on the same spot, right? So you will take value from here as sk for k -1, and that's the expectation is 0.75 or 1.75 if you sum it. Right? And you continue this way, and you are improving the policy. Or improving the value function so that it corresponds to the fixed policy you are computing. Does it seem to make sense? It can be infinite. Eventually, it will converge, maybe or not. So that's the question. So does it make sense? Like, does it look like something that would converge or that would compute the thing we want? Like, does anyone have any intuition why this is a good idea? Like, does everyone understand what it does? It always just like assumes we have computed the value in the other states already, like, well, computes the value for this state based on the current estimate of the value of the others, improves it, and then does the same again and again and again. And I'm saying that maybe it converges to something meaningful. And okay, I can be more bold, and I'll tell you that it does converge to the optimal solution if the gamma is, the discount factor is strictly smaller than 1. And again, this is something which is very often present in the reinforcement learning. So in the reinforcement learning, you are iteratively improving your knowledge, right? The value function is some kind of knowledge about how you should behave. And you want, with every new experience, you want to update it a little bit. And then you want to prove that eventually, if you do these updates, you will converge to the optimal solution, right? This is something you generally want. And the proof of that is very similar, very often. And it's based on something which is called contraction operator. So we are looking at these value functions as vectors because we will want to run functions on the vectors as the input. And you can take some function f, which will take some value function at time 1, which is a vector, and will return a value function at time 2 as a vector, right? That's what this operator was, for example, doing, right? This backup operator we have, like, had on the input some value in time k and return some value in time k plus 1, right? So you can see the whole, like, updating all states as this function f, right? It's some kind of function. And you may remember from calculus, what is a contraction operator? Have you ever heard a contraction? Who has heard the word contraction in like functions? Like the function may be a contraction. At least one? Okay, so the function is a contraction if you take two inputs. You have some x1, x2, which can be some vectors. And you apply those functions, like the function is from the same space to the same space. So let's say that the f is from Rn to Rn, where the n is the number of states in our case. If you apply the f, you will get some y1 and y2, fx1 and fx2. And now the function is a contraction if this distance is always larger than this distance. So for any two inputs, if you take this distance, it will be larger than this distance. Right? So it's a gamma contraction if it's not just closer, but is at least gamma closer, right? So if you take this distance between x and y, and then you take the distance between fx and fy, fx and fy will be at least gamma closer than x and y was. Does it make sense? And then there is a very classical kind of theorem from analysis, which is saying that if you take any contraction and you will iterate it, you will converge to a unique fixed point. So then you will take f of the y, then you will take f of the next thing, right? And from any place, you will gradually converge to the unique fixed point of the contraction. I'll not prove this, like you probably have seen it in some calculus, or you may see it in some calculus books. So how to prove this is not that important, but it's important to understand that for reinforcement learning, like this is super key thing, and very often you use this principle to prove that things work. And you can prove about this operator, which is just updating the value using this expectation, that it is a gamma contraction. If you are interested in the proof, you can just look here into the Tom Mitchell slides. It just takes a norm on this. You can pick any norm you want. So you take L infinity norm, and you will show that at least one coordinate will have to come closer. If you take any two inputs to the operator, then in at least one coordinate you will get gamma closer than you were before, after applying the operator on both of them. Right? So that's just to have some idea how these reinforcement learning ideas work. So you come up with an algorithm, you say that the algorithm is making some operation of the value function, and if you can prove that this operation is a contraction, that for any two value function it will get them a little closer, then you can guarantee that if you apply this operator forever, it will converge to something.
We are talking about the norm of vector with all the states. Like the value vector.
Yes, this value vector, which is like indexed by states, and for each state there is a value, a number. That's what you are like using this operator on. Okay, so here is just the algorithm written in pseudocode. So you initialize with initial value, and for all states you will keep some delta of what was the last change, because you will want to apply the operator not forever, because that's quite a long time. You want to apply it only until the point where the change is not that large anymore. And that you will track by this delta, and for each state you will take the current value, you will update the value using the equation, and then you will update the size of the largest change you had so far, and if the largest change is below some threshold, you will end, otherwise you continue with another iteration. Okay, So that was policy evaluation. That was one step of many reinforcement learning algorithms that you are trying to, you have a policy so far, and you are trying to compute the value for that policy. And you can do it this way, for example. And then what do you next? What do you do next? Like, can you, based on the value, improve the policy? If you take any arbitrary policy, right? You take the uniform policy, for example. You compute its value. And now I ask whether you can use this value function for that policy to improve the policy, to come up with a policy which will be better than the original policy. Mm-hmm. Mm-hmm. Exactly. So if you look at any state and you take the greedy action instead of the action that you were, like greedy policy instead of the policy you had there, you improve in that state, right? Because before you had some probability of going to the optimal action, maybe the probability wasn't 100%, and then you had some probability of going to some other actions. That means that your expected value in that state was lower than it could be if you just put 100% to the optimal action, right? To go to the optimal state. Okay, but you change the policy in the MDP, right? And that's a loopy thing. You will be getting back to that state and so on. Like, couldn't you break the value somewhere else because of this? Like, you could or you couldn't? Yeah, like if we changed it everywhere, but like we can change it only in one state, right? But can it happen that from some other state we want to come to this state, but there we want to go to a different state, right? Like we don't want to make this change for some other path in that MDP. And that cannot happen, right? Because of the Markov property. The optimal thing in the current state like cannot depend on the history. That's the Markov property, right? Like everything that happened in the past doesn't matter. Only the things that will follow matter. So if you improve in the current state, any other policy, any other kind of trajectory that would visit that state will again be just improved by this change, right? So it cannot happen that you would make a change that improve you in one state, but it would make it worse in some other state. That goes against the Markov property. Okay, good. So once you have the value function for a policy, you can look at any state in which you are not doing the best thing, you are not taking the action to the optimal state, and you can improve that, and that will improve your policy. Can you do it in two states at once? Can you take two different states in which you are suboptimal and switch to the better policy? Like, can it somehow interfere? Can you like break it? Or will it like improve in both states?
We should recompute everything. When we change one state, we need to recompute everything to be exact, but we could probably change two states, it would be approximately correct.
Yeah, it's not only approximately correct, like of course the value function will not hold anymore. You will have to compute new value function to have the right value function. But if you change in two different states, like what can happen? Either you will never visit the other state from the first state anymore, and you just keep your improvement, nothing can break. Or you will visit the other state, but you have improved this other state, you didn't make it worse. So you will improve it again, right? So by any change, any combination of states in which you will improve to the better state, because of the Markov property, you will just improve the whole policy. You will improve like the overall behavior in that MDP. Does it make sense? And that's the key observation that drives many reinforcement learning algorithms. So anytime, if there is a situation where a Q pi SA is larger than V pi SA, that means that the current policy in that state is worse than the best action in that state. Some action is better, right? Not even the best, just you'll find a better action than the current policy. Then you can set the policy in that state to that action, and it just improves your strategy. It can never break your strategy. It improves in that state, and if some other state like doesn't go there, nothing happens. If some other state goes there, then it will also benefit from the improvement. And nothing can break if you go to multiple states. So that gives us the already full algorithm for solving MDPs, right? Before we were just evaluating fixed policies. Now we'll be evaluating policies and improving policies. So you initialize value function arbitrarily. Like this arbitrarily is going to be important later, because if you want to use neural networks, for example, then it's very hard to initialize neural networks to all zeros or something like that. So it's good that it works with any initialization at all. And then you go through these two steps. One is policy evaluation, what we were talking about before. So you evaluated policy, and then you have a policy improvement step, where you will take for each state, you will look at it says you will sample an action from that policy. You will find the best action, the greedy action, like with respect to that policy, as the new policy in that state. And if that action is okay, so this assumes pure policies. That's why I got confused. So it assumes that this is a deterministic policy, so you will just take that action that it plays now. You will compute the best action that it should play after. If the action has changed in any state, then you will not consider the policy to be stable. And if the policy is stable, then you finish. If it's not stable, then you go to policy evaluation step. You will evaluate the new policy. And again, you will try to improve it. You will evaluate it. You will improve until after the improvement and evaluation, you will not able to improve the policy anymore, right? The maximal action was always the action you already played. And in that case, you are done. And you have found the optimal solution for the MDP. And again, the fact that these kind of improvement and evaluation converges can be proven through something like this, showing that both those operators are actually contraction and will be converging to something fixed. Okay. So let's take a simple example. So let's assume an MDP like this. And there will be some bad state here, some fail state that you will never be able to get from anymore. So let's start with P0, which will be uniform. And let's first evaluate that. So in the first iteration, we will run the evaluation. We'll have state 0, 1, 2, 3. And at first, we want to just evaluate the state. So we will take state 0. We have uniform probability of going here and here. So with 1/2, we will go here, not pay anything, not get anything, or yeah, -1 for each step. And 10 for getting to the goal. So we will pay -1, and the value will be 0. We will pay -1, the value here will be 0. So the initial value will be, like after the first step, it will be, so initially it's 0, 0, 0, 0. In the first step, will be -1, 0, -1, 10, right? So we'll pay -1 and get to either 1 or 2, which are 0. Here, from 1, we will either go here and get -10 or go here and get +10. So on average, we'll just get 0. And here we have 0, and here we have 0 initialization. So it's 0. Here we'll again pay -1. And in state 3, we'll just go here and get the 10, right? That's the only option, if we have this ordered MDPs. And then, after we finish the evaluation, in state 3, we will have something like 7/2, 0, 9, and 10. Right, so we run the policy evaluation. We evaluate the uniform policy. This will not change anymore. So we can go to the next iteration of policy improvement. So how do we improve the uniform policy to some policy 1? In state 0, we can go here, and here we will get S1. We'll get 0, so it's -1. Here, we'll get -1, and S2 is 9, right? So for P1, we will decide to go in this state down, right? In state 1, for going here, we get 10, and we'll get to goal. For here, we get -10, and we go to fail. So we, of course, decide to go 10 and go right. For this state, we can go right and get the 9 from here. From S3, get the 10 even. And of course, from S3, we will just go to the goal. Right, so this would be our new policy Pi1, which is greedy with respect to the value function of Pi0. And then we continue again with evaluating this policy. And if we evaluate that policy, it would be already 8, 10, 9, 10. right? That's the value function corresponding to that policy, because it goes -2 plus 10 from here. From here it goes just 10. From here it goes -1 and 10, and from here it goes 10, right? And then we would compute BE2, which is greedy with respect to this evaluation, and we already get the right policy, which is the optimal policy. Does it make sense? So this is policy iteration. Yeah, we stop when the policy is stable. That means that after having a policy, computing its value, and computing new policy, the policy didn't change. Right? So you are right. We should still run the value evaluation of this. That will give us the 8 for S. No, is this one. So it's 9 for S1 10, 9, 10, right? And then you compute again the greedy policy with respect to this new value function, and you will find out that this is the same policy, and that's the end. Then you know that like you cannot improve anymore. Very good question. Yeah, like that's what I try to demonstrate here, that it started like with the uniform, then it changed to go down because of this penalty. So it got a wrong way for some time, but then it already found the right solution. And eventually, this is guaranteed to converge to the optimal solution. Yeah, we are not sure. Yes, we are not sure. It can be like look that it's improving. Like the value should be generally improving. But it can be improving at different pace, right? Like it can be improving very quickly, then it can be for a long time, like you will be on some plateau, it will be improving just a little bit, and then you will find something, then it will start improving more. It could happen. That's a very good question. Like, how many steps you should do? Like, it looks a little wasteful here, right? To make many like steps to improve the strategy perfectly, and then run many states to improve the policy. And if you take this kind of example, which is a slightly larger example, right? Again, on our grid world. And you start with the uniform, probably the uniform policy. Then you have this value function in next iteration. This one, right? This is just the policy evaluation iterations. You are improving and improving, but if you look at the greedy policy, what you want to compute from the evaluated like value function, you see that after 3 steps, the policy doesn't change anymore. Right, so you are evaluating the value function to be more and more precise, but it's not very useful because like it doesn't change the policy you will compute from that, and then you will compute like go to the next step anyway. So all of these iterations seem to be like wasted effort. Right? And that's related to what you were asking, like when do you stop? And there is actually a very nice generalized policy iteration like theorem and theory, which is saying that it doesn't really matter, right? You need to make any consistent step to improve the value function. And you need to make any consistent step to improve the policy. And if you can ensure that at least in expectation, you will, in each step, at least by some epsilon, improve the policy, and at least by some epsilon, improve the estimate of the value, then you will converge. Right? So the policy iteration we were talking about, like there is this image which is trying to capture the intuition, like was trying to improve all the way the value function to compute the optimal value function for the policy. Then improve all the way the policy to compute the optimal policy, like greedy policy with respect to the value function. And then again, improve the value function with respect to the new policy. And again, improve that, right? And then you are guaranteed to converge to the optimal policy and optimal value function. But what is super important for reinforcement learning, any consistent step in that direction and any consistent step in that direction will eventually bring you there as well. Right? So you don't need to go all the way. You just need to be like in expectation. You always need to make the step. You need to guarantee that on average you will make the step in the right direction, and that will bring you to the optimal solution always. And that's important for reinforcement learning because you often, like, you don't know the POM-DP, right? You cannot work with all the states. You don't even know what all the states are. But if you are in some state, you have some estimate of the value function, and you can guarantee that you are either improving the value function in that state or you are improving the policy in that state, then you can guarantee that eventually you will converge to the optimal policy. Mm-hmm. In this case, sign of the error, size of the error. So you can see it from the Bellman equations, right? Like if the difference between the current value and the estimate of the value based on the neighborhood is small, and if it's small everywhere, then you know that you are rather close already. If you need to make a huge update, if you find out that somewhere you were completely wrong and there is some other action which is much different than you expected, then you are probably still far from the convergence, right? But again, this is kind of general idea. Like then you will take the very specific algorithm, how to improve the value and how to improve policy. That will create a very specific algorithm, and you can study that, and you can compute convergence rates for that specific algorithm. Like for this general idea, it's hard to say what the convergence guarantees would be. Just that anything that follows it will converge. That's the important thing. So you can take any subset of states, possibly even just one state in which you will improve. And if you just randomly sample one state in every iteration and you improve either policy or value in that iteration, it will converge. If you improve only in expectation, right? So you can make some kind of neural network update, which can sometimes make things worse, sometimes make things better. But if in expectation it makes things better consistently, like you can prove that every time in expectation you make it better, it works. Policy improvement based on one action, small value improvement in the right direction, so you don't need to compute the value functions perfectly. If you just improve it even by some delta, some epsilon, some small number, that works. Okay, so that's a general scheme of things. Like there is this policy iteration, which is the complete thing. Then there is generalized policy iteration, which says that you can make any size of steps. And then there is a value iteration algorithm, which is a super simple variant in which you make just implicit assumption that your policy is always the greedy policy. So you are not tracking the policy explicitly, as we did here, that you would always have some object that will represent your policy. You just assume that your policy is the greedy policy. And you are making your value updates based on this assumption. So if you are updating the values, you will make the following value as the value of the best action. So you will evaluate the value of each action and take the max of it and put it as the new value for that state. We have an example. So at first, the algorithm. So the algorithm is easy. Again, you compute some delta to know what to stop. You compute the current, like you go over all the states. You look at the current value of that state. You compute the new value of that state based on picking the maximal action and taking the expectation of that action. If that change is not too large, you finish. If it is still large, you will go to another iteration, and again, you will go over all the states. Right? So you go over all the states, you compute what was the largest difference you made in any of those states. If that difference is smaller than the threshold, you are done. If not, you go over all the states again. And you are improving the value function and the policy at the same time, but you are not tracking the policy explicitly. You just assume that it's the maximal, is the greedy policy with respect to the value function. Does it make sense? And output is just the greedy policy with respect to the value function. And this is not entirely what I was explaining here. Or let's go to the example to make the point clear. So again, you start with just ones, and then you want to compute the value function for this state. You will look at this values. Everywhere you pay 1 and you get 0, so it's -1. So the value function in the next step will be -1 everywhere. And then if you look at this, you can go here, 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 or stay where you are. You will take the max of it, which is here. You will pay -1 to get there, but you will get 0 there, right? So this is your new value. And after just three steps, it will converge, and then your solution is just to follow the values. So from here you would go here, from here you would go here or here, from here, here or here, right? Then you can be just greedy with respect to value you computed, and that's the optimal policy. Okay. This is not entirely what I was showing. There is one key difference in this algorithm. What is it? This is what we are doing, and this algorithm is slightly different. And it's this one array version. Why does it say one array version? Like in the example, we always had the old state of the value function and the new state of the value function, right? We are always computing each value based on the old state. But here we have just one array, one value function, and we are always like, in any state, we are using the same value function. So we can be rewriting the values during the iteration. Right? If we are here, we compute this -1. Like assume that we are just iterating over all states like this. we computed this 0, fine. Then we computed this -1. And when we are computing this state, we are already using this new value that we computed, right? If we will be computing, like we compute this, here we'll be using this value from this current iteration already. Right? That means that we have the single array version. Can that break? Like again, if we think about the generalized policy iteration, any consistent improvement in policy and any consistent improvement in value will bring us there, right? So you can think of this as separate updates, like separate improvements. Each of that is improvement. So even this way, like you will still converge to where you need. So you can save memory by just having one array and not two arrays and swapping them as the algorithms usually explained and theoretically analyzed, but this works as well and is much more often used. Okay, so that's all I wanted to tell you today. State and action value functions are key concepts in reinforcement learning, and I hope that we got some intuition how they work. Their values in different states are tied together using Bellman equations. Bellman equations can be used as operators. That means that you will just update this vector using that operator, and it's a contraction. So it's guaranteed that these updates will converge to where you need. A key takeaway is this generalized policy iteration, which means that if you improve the policy and you improve the value consistently, you will eventually converge to the optimal policy and optimal value. And even though these algorithms required kind of full knowledge of the MDP, they can be easily kind of generalized to not include the full knowledge, and that's what we'll be talking the next time. It will be basically, again, approximation of this, just based on very limited knowledge about the environment. Questions? Okay, if there are no questions, then thank you very much and see you in a week.